Toby, I have a quick question. Speaking of lab frames, I know there's been tests around interferometry and variances in the speed of light. If you could give a quick, concise, you don't have to go in too deep with it, or go into deep as much as you want. I know you did a presentation on the Sagnac effect corrections and the other correction. Could you? I'm going to go over it to get the arguments down tight, but can you give a overview on what that entails and how that doesn't work where you need something to reference like the Earth or the platform?
Yeah, so you go back to the 1830s. You had a pretty clever, a pretty smart guy, Fizeau. Fresnel. He was able to deduce using looking at water refraction rates that you had what is like around a 70% refraction rate in water, but also there's a 44% translational motion of the water's motion. So if you shoot water through with stream like down a river, it actually goes 44% faster with the speed of the river. And if you shoot it against the river, it actually goes 44% slower against the speed of the river. So they figured it out back in the 1830s, the way in which electromagnetic waves propagate through a material medium, because that's necessary for waves. You have to have a material medium for them to move through. And they figured that out. They figured out the one-way velocity of light in the 1850s. Arago and Fizeau both figured that out. One used a bunch of crazy stuff with diffraction rates of light, or with different refraction rates of light. And the other guy used some cogwheels and shot the light through some cogwheels, and then looked at the pulsation rate of the mirror coming back over. But in any case, they understood the propagation rate at which light moves through a medium, and they understood that medium very intently, or very intimately, right? That's why that's what Faraday figured it all out. That's all of Faraday's experiments, which is how we get to current modern day electrical field theory, were based around lines of force and lines of motion. He understood that things were connected through an innate background. And so we wouldn't have had all those experiments that Faraday did if he didn't understand that. And then when Maxwell came along and took all that and put it to equations, the brilliant math that he put it all to, he once again intimately understood the fact that there had to have been a background medium from which those waves had to propagate through. And so that was all well understood, not questioned. There was no question about was there an ether, is there an ether. And that's why in 1887, when they came along to measure the motion of the Earth, it was a well understood premise. They weren't testing for the ether, they were testing for the motion through the ether through the material medium, which is necessary for electromagnetic waves to propagate through. That's what they were testing for. And whether or not you believe in the ether or not, call it whatever you want, there is a material medium that is necessary for electromagnetic waves to propagate through. So that was the premise of Michelson-Morley. They they split a light wave and they shot it orthogonal, one way north, one way east. Or then you could also do south versus west. You shoot it orthogonal, and then when you split one light wave, so you don't have a different fringe, you don't have any kind of a wave difference, right? It's the same light wave. It gets split in two by a mirror, and then it goes down orthogonally, and then it bounces and it comes back and it recombines. And when it recombines, if there was no difference within the time that it took for the split light wave to go to one end of the end and come back to, go down to the ends and then come back together, if there's no difference in time, that light will be back in phase with itself, and you won't have what's called a fringe shift, or a displacement pattern. The displacement pattern is the fringe shift that's measured when those light waves do not perfectly line back up. There is actually a difference in the travel time out to those mirrors and back in where they recombine. And so you can actually look at that that displacement pattern, that fringe shift, and you can see the amount of you can actually use a model, a regression model, and they knew exactly what they were doing when they set up the Michelson-Morley experiment. That was the premise it was based on. So they shot it orthogonal, and they shot it east-west, and that was supposed to measure the orbital motion of the Earth in its orbital motion, not to be confused with rotational motion, around the sun, right? And that's supposed to be 30 kilometers a second. The device was sensitive enough, it's not the level of precision wasn't really there, but it was at least could detect down to like 2 or 3 kilometers per second. They actually got like a little bit of a fringe shift with it. So they go to measure it, they don't get the 30 kilometers per second. Like they set up this big thing. Like, that's why it's called like the greatest failed experiment in history, because they didn't get a friend shift. And this is all based on very well understood classical mechanics. And they're like, well, this is kind of crazy. Like we put a bunch of like hype into this and money into this. And now we look kind of dumb. And so they sat around for like, what was it, 18 years or whatever. And they're trying to figure it out. There's always theories being put forth. Well, maybe the ether, somehow rigidly sticks to the earth. But then, like people are like, well, that doesn't make any sense, because if it's like, if it's within the ether, then, because we all know you can't have, like, in order to get away from the ether, by the way, you can't just like keep if you're gonna acknowledge the fact that that ether is the necessary medium, the material medium necessary for electromagnetic waves propagation. If you're going to acknowledge that fact, then it has to exist within all of quote unquote space. So you can't have the vacuum of space and then also still invoke that. Those things don't really work too well together. That's why finally 1905, they're just like, let's just like throw the whole ether thing out. Einstein comes along, says that 1 + 1 does not equal 2. Like a little, like 0.9 speed of light plus 0.9 speed of light does not equal anywhere close to, it's still under speed of light. 1 + 1 doesn't equal 2. That's what Einstein told us. And we all said, oh, okay. It was all based on, he literally says the words in 1905 in his paper. He says, based on this imaginary physical experiment, an imaginary physical experiment, he invokes, he uses his clock synchronization method. There's just this arbitrary method. He's trying to get away from the idea of an absolute space and an absolute time, because literally you have to step out of reality to then say, oh, well, we can't actually measure the motion of the earth through absolute space, or what they would say, or what we would say, the ether, the material medium necessary for electromagnetic waves propagation. And so he took all that, flipped it all upside down. Instead of acknowledging any longer that everything is infinitely connected and that everything exists within a background medium, and that everything is actually, you take the atomic model, you flip it upside down. Those little points that you see, that you think about, that they have as those little spheres, those little protons and neutrons and electrons, it's the inverse of what you think it is. Those are the counterspatial points in which the intersections are occurring. Those are the phenomena of the field perturbations. That's why they're so hard to predict. That's why they don't have a speed. That's why they have to use double Lorentz boosts, or a coordinate, or a coordinate system rotation, in order to even make the speeds make any mathematical sense, because it's not an electron, it's not a proton neutron, it's an inversion of all that. It's all exists. Everything is infinitely connected. Everything is not infinitely disconnected. And so that's what Einstein did in 1905. He came along and said, 1 + 1 doesn't equal 2. Everything is infinitely disconnected. There's a vacuum out there, and there's these little photon things. The light's actually a particle that's flying through space, and that's how it gets through a vacuum of nothingness. So that was what happened. They said it was no result, right? Like they're like, okay, we didn't get the orbital velocity. The thing was, the device still measured something. There was like a tiny bit of a fringe shift there. Guy comes along, Dayton Miller, and he's like, well, that's really freaking interesting. Like, so you're telling me that light goes faster one way than the other on the Earth? And guess what? It's no difference north to south, and there's no difference north to south. The light speed is the same, but east to west, it goes faster west to east, and it goes slower east to west. Or I have it backwards. But in any case, the Dayton Miller comes along and he's like, well, that's crazy. Let's start measuring that. So he actually takes the Michelson-Morley interferometer, and he adds a bunch of mirrors to it. So basically, he just increases the amount of the amount of length of distance that the light's traveling before it comes back and recombines and gives you the fringe shift. So what that does is it makes the device more sensitive, because the more distance that you have, the more time that's being invoked, and the more distance and time, the more fringe shift, the more proportional fringe shift that you can get. So he comes along, and the dude just starts measuring like mad, and he's figuring the thing out. Like he didn't just come up and say, like, I'm going to take a measurement of the interferometer. He's like, let's figure this thing out. Let's figure out exactly what's being measured here. And so he starts measuring it more and more, and he realizes, like, wow, there's something very real being measured here. But if you put it underground, if you put it in metal shielding, it seems like there's less of an effect measured. And so after while he's figuring all that out, he's taking measurements, and then he kind of learns how the thing works. And so then he's like, all right, I need to go to high altitude. I need to take measurements at altitude. So he goes to California, to the Mount Wilson Observatory. And remember, This is all based on what they said was nothing, and when they what Einstein said was a null result, because now we can't have any. I mean, I didn't even get that much into how the fact that they had to say that literally the speed of light is constant, and that is like, because the fact that the Earth is in motion and they couldn't measure that motion, they had to say that the speed of light is always the same. Like, it's a fantasy land. There's never been substantiated. It's so unsubstantiated, like you literally can't substantiate it by matter of fact. You can't substantiate it because it only exists. It's only constant outside of reality. Like, you measure a fringe shift with a Sagnac device, like a rotating little Sagnac device back in 1912. Georges Sagnac threw a big old wrench into the whole freaking thing, because Georges Sagnac comes along and says, like, dude, you guys, I think you're wrong. I just rotated this little device here, and there's a fringe shift proportional to the speed of the rotation. Like, I think there's an ether drag occurring. That doesn't really make sense with what you guys are saying, that the speed of light is constant. And they're like, well, that's a rotational vector, Georges Sagnac. Let's go ahead and burn all your papers and never translate any of them to English, and make sure that the one translation that we do get, if anything that you ever said, is from this random dude that doesn't even appreciate your work. And so, we get a one random mention here or there about how you measure differences at altitude, which already throws the whole thing out, but that's all burned away. Can't find any of Georges Sagnac work out there about that, which, by the way, if anyone finds any of Georges Sagnac's original works, please send them to me or Alan. Like, we've been trying to find them. They don't seem to exist anymore. But in any case, so Georges Sagnac, there's a big wrench in the whole thing. So then a few years later, like 8 years later, whatever, they're like, okay, well, we're going to do our own interferometer design. We're going to do a big one, and we're going to measure the Earth rotation. And forget everything we said before about the orthogonal measurement of the orbital rotation, because they knew what Dayton Miller had been measuring all that time. They're like, well, let's go ahead and get on top of this before this guy exposes how, the philosophical conundrum that we're in. So they say they measured the Earth rotation, and they put it underground, and they had these big long tunnels that they did the orthogonal setup with again, and then they measure a fringe shift. For some reason, they acknowledge the fringe shift there, and they say, okay, that's Earth rotation, and then they leave it at that. But Dayton Miller didn't just leave it at that, because Dayton Miller knew that that's not even the proper way to do it. If you actually want to get the sensitive measurement of that actual fringe shift, then you have to take it to altitude. So let's go back to him when he went to Mountain Wilson Observatory in California in the 1950s or 1920s, excuse me. He starts taking measurement after measurement after measurement. And this is after he already knew how the device worked really well. And he'd gone through tons of criticism, people saying, oh, but you're not counting for the heat fluctuations. Oh, you're not counting for the vibrations of the people walking outside. You're not accounting for the pressure differentiations, blah, blah, blah. And every single time, Dayton Miller's like, got it. Okay, let's test that. Because one other thing Dayton Miller measured, very, very, very important to this whole thing, there's a periodicity to the interferometer speeds, the measurement of that orthogonal motion, or the orthogonal speed of one way versus the other. That changes daily. It goes up and down. There's a certain timing to it, of a fastness and a slowness. It speeds up and slows down, and that happens year to year to year. Yuri Galev went through and measured. This is a guy from in the 2000s. He went and measured and found. He looked at Dayton Miller's results. He looked at his own results, and he found, like, holy cow, that daily thing is, like, very well corroborated. And it's crazy, because not only does it happen every day, but if you look at, like, August 18th from 1920 something, and then you look at August 18th from 2000 something, you get a very similar daily periodicity to the ether wind fluctuation. But anyways, back to Miller. What Miller meticulously tested was the periodicity itself. Because he saw, okay, the heat affects things, the pressure fluctuations affects things, the vibrations affect things, and that's hard to account for. But I'll do everything I can to account for those. But regardless of what any of that stuff is doing, the periodicity is always there. And that's two different levels of periodicity. There's a space effect, which is just the daily periodicity that I just was talking about, but then the equinox effect as well. There's a periodicity that matches the correlation of the equinoxes. So when the sun is at its minimum and maximums, that shows in the fringe displacement of the preferred directionality of the quote unquote speed of light. That is relevant to where the sun is in the sky. It does not match an orbital motion. It matches a what I would call Earth time motion. It's the time we exist within. The closest thing we could get to an actual measurement of time comes from the sidereal. Oh yeah, so back to Einstein with his insane crap about the 1905 when he made the whole thing up because he had to get away from an idea of an absolute time. He says, oh yeah, if you just take a bunch of clocks, a bunch of atomic clocks, and you sync them all together, that's absolute time. I mean, there is no absolute time, but all those reference frames, they'll all stay in sync. So those reference frames, you can use those to measure other things against. But then those clocks start moving around, and holy cow, what do you know? Those clocks don't even stay in sync with each other because the way that they're designed with the cesium oven and the electrons that have to be shot in a loop to make it back to the sensor so that they can actually take the readings of the frequency of the cesium oven. In order for that whole thing to work, it relies on electromagnetic waves propagation. So as you move those atomic clocks around, they go out of sync with each other. And what do you know? All these clocks are out of sync with each other, but there's no absolute time. Einstein, what are we going to do? There's no absolute time. Everything's out of sync. But we need to get everything back in sync so we can actually have a functional GPS system. What do, Einstein? Well, maybe we can sync them to absolute time. We can look at the sidereal time, the absolute motion of the stars, and sync everything back to that. And then we can just pretend that we never did it and just pretend that Einstein made any frickin' sense, which he never frickin' did. And so the whole thing is bunk from the start because you have to invoke an absolute time. And then when Sagnac comes along and does his little interferometer, the people that are actually thinking about it, they're like, well, we need some kind of relativistic explanation for this. What are we going to do? And they're like, oh, well, there's a Lorentz transform. Let's just Lorentz transform what we just measured in front of our face. The fringe shift that's directly proportional to one way or the other. Let's just Lorentz transform it. Who cares if we can't make it has no predictive value whatsoever? Let's just Lorentz transform it. And then when we can say that's a rotational vector. That's a rotational vector. It's a loop. It's a rotational vector. We measure earth ball go spin, rotational vector. Don't worry about it. Don't worry about it. Don't worry about it. Oh, but then Ruang Wang comes along in 2004 and he understands how GPS works. He wrote a paper about that. And it's like, well, GPS actually relies on the one-way radio wave propagation. So you've got a big old problem right there. But that's kind of complicated for some people. And you really need to show it to them in a little local interferometer. So let's do it. Let's just test the linear velocity stuff, right? Hey, Naval Research Laboratory, I've got an experiment I want to do. Oh, thanks for the money. Thanks for the funds. Okay, let's set this all up. Let's measure linear velocity because they say it's rotational vectors. So let's move the fiber optic cable, the wave core fiber. Let's move just that in a linear vector. So they move just that in a linear vector, and as that moves in a linear vector, the fringe is measured directly proportional. Holy cow! Earth ball goes spin. But then what are we going to do? Because there's a linear vector being measured. So if the linear vector is being measured, then the Earth ball goes spin things. No. Let's Lorentz transform that too. We can Lorentz transform that too. Let's just have some just another paradox. Who cares? Just another paradox. It's not a big deal. We got particle wave duality paradox. We got the twin paradox. We got the Einstein Rosenberg whatever paradox. We got the this idea of this cat in a box that's got food to eat, but the food's poison, so the cat's dead and alive in a superposition. Like, who cares if it's a paradox? Just Earth ball go spin. Forget about the GPS. Forget about the fact that GPS is actually beautifully built on a system of eloquent classical mechanics that rely purely on the idea of the speed of light not being constant. Guess what? You take that out of there. Actually, you take just the preferred directionality of the speed of light out of there. The whole thing goes off by 30 meters. Like, oh, I'm actually down the street from where I am because I couldn't acknowledge the gradient of velocity or the velocity gradient that that electromagnetic waves propagate through. So anyways, hopefully I think I got everything in there. Hopefully that answers the question.
Receipts can be found at Ether Cosmology. Thank you for that, Toby. I knew you would go off.